So here at the bottom of these slide, I draw a a timeline chart where time is efficiency, and you of course you see how QMC, while being a very accurate and systematically improvable method, is at the bottom of this sequence of possible choices. We have QMC, possibly DFT, and the most efficient way would be to use, of course, a classical potential at the expenses of accuracy. And the idea is, can we use machine learning to learn how to perform an ab initio simulation and use such machine learning potentials in molecular dynamics simulation? We are going to, this question about constructing machine learning potential has been around for some time now, and I'm going to focus on QMC as a target method. Because QMC is a systematically improvable method, and it does not depend on any specific approximation. And also within the variational framework, we have the possibility of computing forces, which are very important observable to computing for molecular dynamics with a joint algorithmic differentiation, and so in a very efficient way. So one can prove that computing forces only takes up to 4 times the computational cost of computing energy. So we have a good scale. The drawbacks of quantum Monte Carlo is that while the scientific community and the quantum Monte Carlo community has made a lot of effort to improve the efficiency, the scaling, Monte Carlo is still a very expensive method, especially if one wants to employ it in molecular dynamics simulations, and to study large system and performing very long simulation. So here you probably understand why the importance of having some machine learning model which can somehow accurately reproduce QMC observables in order to make QMC molecular dynamics feasible. And the main point that I want to stress here is that we cannot just choose any machine learning model. So, and the point of this is the following: if we were able to just choose any method, we could, that would mean that we could probably have the possibility of having large and huge training data sets. So I will talk about this in a few moments. But the idea is that we want a machine learning model which is able to learn as well as possible with the smallest amount of training data. And that's because if we wanted to do if we wanted to use a machine learning model which is able to learn only with very large data, then we would have to perform I don't know, hundreds of thousands of quantum Monte Carlo simulations. And at that point, we might just do ab initio QMC molecular dynamics. Given that one, of course, before trying to reinvent the wheel, has to look for alternatives and for the efforts that have been already made in the scientific community. And machine learning potentials have been constructed in the literature with mainly 2 techniques. The first is neural networks, and the second is kernel regression. So, as you might know, neural networks have been, have seen a tremendous success in the last years in the most diverse fields, computer vision, natural language processing, and so on and so forth. And as a result of this, many researchers, both from the theory point of view and the implementation point of view, have put their effort in improving the state of the art. And so we have many optimization techniques. We have ways to perform fast training and fast inference. And the nice thing about neural networks is that the number of weights that describes the neural network does not explicitly depend on the size of the training set on which we want to train the model. So if we were to, of course, the performances are going to depend on the size of the training set, but the explicit number of parameters is not. So we can have, I don't know, a training data set composed by 100,000 configurations and have a neural network with only, I don't know, 10 weights. Of course, this is not going to perform very well, but this is something that in principle is feasible. The development of deep learning in all the fields of science basically have drawn a lot of attention also in the physics community, and it's not surprising that there are already a number of frameworks, deep learning frameworks that have been specifically designed to construct machine learning potentials, such as DeepMD or N2P2, just to name a few. The cons of neural networks, or the ones, let's say, that I can that I'm going to mention for this specific problem that we want to tackle, are first of all the fact that we can, during the optimization, so the training phase, we can incur in local minima, because of course the optimization is not going to be linear. And most importantly for our case is the following. So even in the literature, we see a lot of successful deep learning, machine learning potential, but most of the times the size of the training sets that they require are huge, especially for our case. So we would have to perform, as I said before, thousands and thousands of QMC simulations in order to get a number which is large enough of configurations so that the neural network that we train has good performance. So on the other side, we have kernel regression, and with kernel regression, I'm going to start from the cons. So as opposed to neural network, the number of variational parameters that we have to optimize in kernel regression is explicitly dependent on the size of the training set. And you see how in our formulation, this is going to be something that we need to really take care of. On the other hand, it has been seen that kernel regression performs in general better for smaller data sets. So in a way, we can achieve, as I stated here, a good compromise between good performances and size of the training data, which in our case is somehow a limiting factor. And something that I also want to mention is that, and that we'll see explicitly in the next slides, is that the optimization that we perform, so the training phase, amounts to solving a linear system. And for this, and this is good because we don't incur into local minima, and we have some nice and efficient computational techniques to handle this. So what did we do? Well, first of all, we tried some frameworks, and we were not really happy with the performances. So we then decided to build our own framework. And the ingredients of our framework are the following. So we decided to use kernel regressions for the reason that I just outlined. And we use kernel regression in combination with two fundamental approaches. So the first is the Beller-Parinello ansatz, which describes how we can decompose the energy of the system, and the second is the so-called delta machine learning approach. So the BP ansatz, which is how I'm gonna call this decomposition, has been around for quite a while. I think now it's The first paper was in 2007, if I'm not mistaken. So it's been around for some time. And the idea is that we can decompose the total energy of the system as a sum of local energy contribution. And as you see here, the local energy contribution, there's one for each atom in the system, and such a local energy depends only on the local environment. So we put ourselves around atom I, and we look at what's around atom I within a certain cutoff radius. So a picture of this would be as follows. So imagine this is atom I, and this is the prescribed cutoff radius that we want to employ. Of course, this quantity is very much system dependent and has to be handled very carefully. But assume that we have chosen one. The ELOC that I wrote here is going only to depend on those atoms which lie in the sphere centered at the atom I and within the with radius RC. So this is the first ingredient of our approach. So the second approach, as I mentioned, is the so-called delta learning approach. And again, the idea is to write the total energy of the system as marked sum. Let me phrase it like this. So E tot is the total energy of the system, and we decompose it as a baseline term plus some EML. So what in practice do we want to do here? So E tot is going to be our target method. So in our case is going to be VMC, and E base it can actually be anything, but for our case it's going to be another another ab initio method, in particular DFT. And so where does machine learning come into the picture here? Well, it comes into the EML part of this decomposition. So the idea is that we use machine learning to learn a correction that enables us to go from the baseline method to the target method. And again, as I stated before, this EML is decomposed as per the BP approach and depends only on local environments. So, why would one want to do that? The idea is that this delta machine learning approach makes the learning problem easier. And if a learning problem is easier, then it's going to require a smaller amount of data, which is something that is very important in our case. So we'll see just in a few minutes how this is our starting point. But in theory, there is no let's say there's no constraint on what E tot or E base should be. And theoretically, one could say, okay, I want to start with E base as a DFT simulation with a certain function like, I don't know, LDA. And I want E tot to be, again, a DFT simulation with performed with PB function. And I want to learn a correction term that enables me to go from LDA to PB. So from the computational point of view, this does not really make sense because we're not really saving much. But it's going to be useful for a reason which I'm going to explain in a few minutes. Instead, if E tot is some highly it's a very costly computational method such as BMC, and well, at least compared to, for example, DFT, then assuming that the cost of computing or the cost of inference to compute the correction term is negligible with respect to E base, then the cost of computing E tot, which is a target and computationally heavy method, becomes the cost of computing, essentially of computing E-base, which is a cheaper, in terms of computational cost, a cheaper method. So this is the second. This is the second ingredient, and you're probably still wondering where kernel regression comes into the picture, and that's exactly how we model the local energy term in this sum. So in this slide, I'm just trying to stack all the three approaches that we're trying to mix. So we perform this delta machine learning decomposition, and we say, okay, this EML, we again decompose it as a sum of a local energy contribution, and we model these local energy contributions as a linear combination of these quantities. So the local energy that we want to predict is around atom I, and so it's specific to local environment Ri, and we model it as a sum of kernel similarity measures between the local environments that we have in our training data set and local environment Ri, weighted by some variational coefficient. And the point here is that those variational coefficients are the ones being optimized in the training phase, so are the ones that we want to learn. So of course, and then everything should be clear by now. What I haven't said is, what I haven't said is how these kernel should look like. And the way, and again, this is something that has been already studied in the literature. So the way we model this kernel is through the SOAP, the SOAP similarity kernel, so smooth overlap of atomic positions. And again, this is something that has been around for a while. I don't remember the exact year in which the first paper was published, but it's not something new. And bear with me for a second. I'm just going to ignore normalization constants here, because this is not quite my what I want to stress here. So if we ignore the normalization constant, then we can write the SOAP kernel in this way. So we want to assess the similarity. So how local environment I and local environment J are related or are similar. And we do it by integrating those two densities. Forget for a second this U term and this integral here. So we integrate these two densities, and each of them is defined by this formula. So the idea is that we put a Gaussian term at each of the atoms that we see in our local environment, and we sum all those Gaussian by a cutoff function, which basically realizes these constraints. So this F that I mentioned in my slide below is going to be vanishing outside the sphere of radius RC, and a maximum at the center of the sphere, and in a smooth way, of course, because we want to preserve differentiability of the entire function to be able to apply algorithmic differentiations to compute forces and therefore pressures. And then one might say, okay, let's just consider this integral, and somehow this integral is maximum when the two densities are the same, and so in a way it does already assess some kind of similarity between local environments. The idea is that we also want to enforce invariance of these similarity kernel with respect to symmetries. And so this is why we integrate these. So we basically compare local environment I with all possible, let's say, rotation of local environment J, and we have to average over all of them. And we perform this by doing this integral over the continuous group of symmetries of the 3D space. So this is the general and the original definition, up to some, again, normalization. And the point is that from the computational point of view, in order to compute this similarity kernel, so this is, this part is fine because it's a product of quotient and we know how to deal with it. The point is that we have to integrate over a continuous group, and this is non-trivial and requires to perform a lot of calculations, which are expensive. And to be honest, I don't really know a lot of much of those calculations. So what we decided to do is to take a discretized SOAP kernel, and you see that this formula here is very similar to the one above. The main difference being that instead of integrating over the entire group, we are just summing and let's say integrating over a discrete subgroup of all the possible symmetries of the 3D space. And of course, this is important because the you see that writing computing a sum of this kind is going to be much more computationally effective. It can be easily parallelized, so we are somehow safe from the computational point of view. Again, we are not. This is. This has the counter effect of not ensuring global, the full symmetry invariance. But we notice that this doesn't seem to hurt much the performances of of our model, and I will say a few words later. So once we're here, one should say, okay, we are just ready to to train. This is not quite true, because remember that using the Beller-Parinello ansatz allows us to identify as an atomic. I'm abusing the word atomic, but bear with me with a second. Allows us to identify the atomic component of a training set, not the entire configuration, but the one local environment. For each, all the local environments of all the configurations. So say if we have, I don't know, if you are studying a system with 100 atoms and we have 800 of such configurations, then the model is going to have 100 times 800, which is 80,000 parameters. So this is quite a lot of parameters, and having a lot of parameters can be quite harmful, especially if your training set is not large. So this is, and why should this be bad? Well, first of all, as I stated, and as you see from this formulation, we have one variational parameter per local environment. And so optimizing such variational parameters and performing efficient inference, which is what we do when we use these machine learning potentials in molecular dynamics, is going to be quite difficult. Well, not difficult, but surely is going to be very, very expensive. And at the same time, there's a very common machine learning phenomenon, which is overfitting that could happen. So especially with small training data. So the idea is that we might be able to perform perfectly on our training set, but we might not have generalization power. And having generalization power on unseen configurations, so being able to accurately predict unseen configuration is very important in our case. So we need to eliminate the local environments that we don't need somehow. And the technique that we employed is, well, we have called it local sparsification. I don't think, well, the sparsification term, I don't think it's new. We just introduced this local adjective for a reason, which I'm going to explain now. So the idea is that we want to throw out all the useless local environments. And what does and what makes a local environment useless? Well, assume you have a bunch of local environments in your training data, and two of them are exactly the same. Since the model does not know how to let's say choose between one of the two, we're going to have both local environments, and both we're going to have two variational parameters. So we want to have the most diversified set of local environments of the smallest size. So and again, here we employ to do that, we employ the farthest point sampling algorithm, which is again something that had already been done before, but we do it not just at the configuration level. So we don't preserve or throw away one single configuration, which in our case amounts of n local environments, if n is the number of atoms in the system. But we somehow pick and choose the local environments, and we might just choose one local environments from one configuration, two local environments from another. So we make our selection at a finer level, and this helps us quite a lot. And the idea, well, I'm just going to be very brief here. The idea of farthest point sampling is that we start from a random point, which means a random local environment in our training data set. And then this is going to be the start of our design set of local environments that we want to keep. And then we keep adding to these design sets so that we ensure that the highest diversity within those designed local environments is kept. And at some point we stop with, and we can choose multiple criteria that we can employ as a stopping criteria.
I have a question.
Yes.
This is David separately. But if you just suppose you choose a local environment, but you're going to do a quantum Monte Carlo calculation for the forces, don't you have to do the whole configuration? I mean,
yes. That's
the whole configuration. But what do you save by having different local environments?
In here, in this case, I'm assuming I already have a training data set, and I want just to pick and choose some of the local environments in the configuration. So the idea is, of course, that I still have to do the entire. I still have to do the VMC QMC simulation for the entire configuration. But if you look at this at the formula of the here at this formula of the local of the local energy, there is no need for the number of training local environments to let's say to all be in one configuration. I don't know if that's clear.
So you're saying on the machine learning part, but you don't save any time in the quantum Monte Carlo.
So so for sure we're going to save on the machine learning part. Whether we save on the quantum Monte Carlo, I'm going to address this in probably the next slide. So let me just go back. So as you pointed out, and I thank you for the remark, we save on the machine learning side. And so how much time do I have? I think 20 minutes. Is that correct?
You have 18 minutes.
Okay, thank you. So before addressing that, let me just wrap up on the technical aspects, and then I'll try to answer your question. So I just want to point out that the const function that we employ is the sum, or is a weighted sum of mean square errors of the observables that we want to that we want to train our machine learning model on, and that we want to predict, plus a regularization term. And so I'm with the HECT. I'm just referring to the machine learning model, and with the alpha, beta, gamma, and delta are just weights and parameters with which we can use to somehow, let's say, give some preference to the observables that we want our model to be best performing on. And but the main point is that this function is just a quadratic function on the variational parameter, and if we want to find the minimum of this function, this will amount to solve a linear problem for which we have very efficient and distributed techniques. So yes, again, just a few remarks. So we believe we have a reasonably fast implementation of this SOAP kernel, especially with this discretization approach, and something that I have not seen in other kernel regression methods. We have a hybrid OpenMP NPI protocol, which enables us to scale quite well with the size of the training set, both in the training and inference phase. And we have extended our code to handle generic periodic boundary conditions and multi-species system, and we want to open source the code and interface it with the standard MD tools. So in general, the workflow that we employ is the following, and I think here I will try to answer the question of whether this sparsification problem saves us the quantum Monte Carlo cost. So we choose the target method, the model. In our case, the model is fixed to be training to be kernel regression. Of course, we have to start with a certain actually, so we have to start with a certain with a training set. Okay, so this training set might come from a molecular dynamics simulation, or with a different ab initio methods such as DFT, and on these training set. So at this moment, we have not yet performed any quantum Monte Carlo simulation. On these training set, we perform these local sparsifications, and we have seen, but with in our case, that the local sparsification throws out, even if it's able to save just local environments, it happens that it throws out a lot of configurations. So on the configurations that we save, and bear in mind that not all of the local environments in this configuration will be local environments corresponding to variational parameter. On this configuration, we can perform quantum Monte Carlo simulation to have an actual training set to work on. And then we are basically in this phase where we just employ the standard machine learning procedure of test and validation, cross-validation to tune the hyperparameters. If we believe that we have reached a good enough machine learning model, then we can start molecular dynamics. And here is somehow another benchmark of whether our model is good enough or not. And that's because when performing molecular dynamics, we have a way to assess whether these new incoming configurations on which we are going to predict the observables are known or not to the model. And we have a quantification for how to do that. And the idea is that if the model detects that this configuration is too different from the ones that it has already seen, then the molecular dynamics either stops or does something. But the idea is that we dump these configurations, and these configurations are going to be a part of the new training set that we have, because basically we know that these are unseen configuration and that our model might not perform very well on those configurations, and so we want to integrate such training set. And so we somehow perform a loop here. And of course, performing a loop here amounts again to doing some local specification, and might end up finding out that we don't have to again perform quantum Monte Carlo on all these additional configurations that the molecular dynamics told us were unseen, or were at least yes, let's say unseen by the model. So this is I hope this somehow gives you a general understanding of why these local specifications should somehow save not only on the machine learning side, but also on the quantum Monte Carlo side. So in the remaining time, I want to mention where we applied these frameworks. So we just we employed some known techniques together, and we added our own let's say tricks. And we wanted to study high pressure hydrogen as a very, let me just add here something that is not written, as a very challenging test case. So of course, you probably all know much better than me the importance of studying hydrogen at high pressure, especially in astrophysics and planetary science. And in these studies, understanding the properties of of hydrogen in with experiments is very difficult, because we are at very at conditions which are very difficult to realize in experiments, and so simulations become of paramount importance. And the striking thing is that different methods lead to quite different phase diagram, and so there is quite an ongoing discussion on this topic, especially if we want to focus on a small region of the phase diagram. We studied, or at least we used the liquid-liquid transition of hydrogen from the molecularly insulating liquid phase to the metallic atomic liquid phase as our benchmark test, to test how whether the physics that was coming out of our machine learning model had some sense or not. And there's been a number of papers, even very recently, dealing with this system around this transition. And as you see here, there are a lot of proposed transition lines. While tackling a difficult problem, or in general, while tackling any problem in this kind of framework, one has to ensure that the model that one uses in this context passes some sort of sanity checks. So first of all, since we are using this the delta machine learning approach, we have to ask ourselves, is the final model, so this E-base plus EML, dependent on what the E-base ab initio method, or the E-base model, which in our case is an ab initio method, is? Because of course we don't want the physics, and first of all the model, and second and more importantly the physics, to change as the baseline model changes. Second of all, and again this is very specific to our quantum Monte Carlo case, we want to assess whether the accuracy of the model is somehow affected by the presence of noise. And quantum Monte Carlo observables have a systematic noise, and we want to see whether this noise somehow how this noise affects the physics of the that is predicted using this machine learning potential. And so this is a brief account that tries to answer these two questions. So first of all, regarding the first question concerning robustness with respect to variation of the baseline model, we performed several simulations, and the idea was, okay, if we start with the two DFT simulations with different functions, say PB or BLIP, And we learn the respective correction terms in order to predict VMC. So bear in mind that in this case, our target met, our ethod is always a VMC energy. And the question is, does the transition lines that we see in these different cases change, and if so, how do they change? And you see here that this is the result of molecular dynamics with different potentials. So we performed two ab initio simulations. The red one is DFT with Bleak functional, and the blue one is DFT with PB functional. And we then learned the corresponding correction terms. And the nice thing that we saw, and thankfully, we saw that the two final models, which should both be VMC, were very producing some very similar physics, and very much compatible within error bars. To answer the second question, we had to do a trick, because you just cannot cut out and you take out the intrinsic noise that a quantum Monte Carlo observable has. So we devised the following simulation. So for this case, our target ground truth is an ab initio simulation, which is the one depicted the transition line with ab initio PB simulations depicted with blue squares. And what we did was, okay, if we start with, we want to apply delta machine learning, we start with an LDA functional, and then we try to learn the correction, okay? So in order to go from LDA to PB, and the question is this correction good? I mean, is the correction good? So can we let's say reconstruct the PBE physics starting from the LDA? And this is depicted in the, let me see, yes, in the LDA, in the LDA plus non-noisy ML line. So these dark green triangles. As you see, there is the LDA line does not present a plateau in this density range, while the PBE does, and so does the let's say LDA plus non-noisy machine learning. We then say, okay.
Just give you a time check, 5 minutes.
Okay. Yes, I should be. I think I will finish on time. Thank you. Yes. So what we then did, in order to assess again the robustness of the models with respect to the presence of noise, is we introduced some artificial Gaussian noise to the PBE observables. And the order of this noise was of the comparable to the average noise that we had on our VMC data, which, for example, we employed in this case. And we then learned this machine learning correction that should whose purpose was to go from LDA to somehow a noisy PB, which we used as a proxy of some quantum Monte Carlo simulation. And again, as you see here, those again the physics seems to be captured well, because again we can detect a plateau, and the correction is doing something quite meaningful, because we go from this transition line to a transition line which is very close to the ground truth, which is our ab initio PB. And just for comparison, I'm now I've plotted here these these actually not third but fifth transition line that was constructing using a neural network machine learning potential with DFT PB target, which was published in Nature two years ago. And again, as you see here, this line is this light green circle line is, well, the physics that it captures does not see this plateau that is indeed detected by our machine learning model. So yes, I only have 2 minutes, so well, I'm gonna skip this slide and we can go back to it. But I just want to mention that with this machine learning potential, we assess the transferability of our model. So can we predict on can we train on a certain size system, like a system with 128 hydrogen atoms, and meaningfully predict on a system with 1024 24 hydrogen atoms? And as you see here, the energies and the energies per atom and the pressures that we predict in the two cases seem to be pretty consistent. So this is duplicate. So this is so these are the transition lines that we got from our molecular dynamics ML QMC powered simulations, and this is, well, the red circles are, let's say, our contribution to this part of the to the phase diagram. And we see that we have a decent agreement with previous MD simulations performed with VMC, which is these light green square lines performed by Mazzola, Sorella, and collaborators. We have some discrepancy with other Monte Carlo methods, and we are still trying to understand. So I'm referring to these dark green squares, and this is something that still has to be explained. We believe we have some good consistency with experiments, and yeah, I mean, just to wrap up, somehow we were trying to reach a good compromise between size of the data set and so computational cost of getting the VMC configurations and accuracy of the model, and I think we were able to do so. Well, I'm going to skip to the to the perspectives. We can talk about it, and again to some preliminary results. I just want to thank my collaborators, especially Sandro Sorella, who was the initiator and a huge contributor to this project. And I thank you all for your attention.